in a couple minutes.
Oh, okay.
So you try to share your screen, try to
Sure.
do
Yeah, let me do that.
and I would like everybody to open the FireGrader for ACID presentation. His topic is time synchronization problem in distributed computing. And while he will be speaking, you can move those sliders to provide evaluation, and then hit submit. You can submit multiple times. The newer evaluations will override the previous ones.
Is everyone will able to see my screen?
I can see it, yes.
Yes.
Other guys on phone?
Yes.
Okay. Okay. Should I go ahead, Simon?
Yes, go ahead, please.
Okay. Good morning, everybody. Thank you very much, Simon, for giving me an opportunity to present myself. So basically, today I have chosen the topic like time synchronization problem in a distributed system. So basically, like there are various kind of problems we are facing, and what kind of solutions we come over through this problems which is occurred in the distributed system. So this presentation is about that. So first we will talk about the what are the problems, and then we'll discuss about the solution part of it. So let me start with the presentation. So okay, so let me talk about first what is time synchronization. So basically, time synchronization is like a process to bring their clocks close together by using the computer system. Even initially, when the clocks can be set accurately, real clocks may differ like some amount of time, whether it's a millisecond or microsecond, and there is a like clock drift caused by clocks counting time at slightly different rates. So like there are several kind of problems comes in wherein distributed systems will try to like we can see the difference of clock rate differences between two machines, and because of that there are a couple of challenges come in the real world to synchronize the time where you need those kind of systems where you need some kind of global time. So like and in every aspect wherever which industry we are, like time is very important, and that's like very important and interesting kind of issue in distributed system. And there are several reasons for that. So like first one is like time is a quantity. We often want to measure it accurately. In order to do that, like what time of a day a particular event occur for which particular computer, it is necessary to synchronize its clock with an authoritative and external source of time. Like let's take an example of like e-commerce transaction, which involves like it involves the merchant's computer, it involves the client computer, and as well as it involves maybe the banking transaction, then their computer is also involved. So here in this case, let's say something goes wrong or something went wrong, then you might need the auditing process to be done. So at that time something goes wrong with your transaction, maybe that auditing part, the timestamp is more important of it. So like that is one part of it. Other challenges or other problems we can get it is like if our accurate or reliable time is necessary for like financial or legal transaction system, even in transportation or distributed system or many other applications involving distributed system or resources, needed time to be properly synchronized, or as much as like they can synchronize exactly. So for distributed like internet applications, and accuracy and reliability of a clock device is also required for that. And in that, there is one aspect is like a room temperature for like quartz oscillator may drift as much as like second per day. So like these are one of the things like which may lag the times. Like in clock synchronizations also deal with understanding of temporal ordering of events produced by concurrent processes. It is useful for synchronizing senders and receivers of messages and controlling joint activity, and serializing concurrent access to shared objects. The goal is that like multiple in unrelated processes running on different machines should be in agreement with and be able to make consistent decisions about ordering of events in a system. And like for these kind of events, we introduced a concept called a logical clock, where the clock need not have any bearing on the time of the day, but rather be able to create event sequence number that can be used for comparing set of events such as a message within a distributed system. Like another one of the aspect is like it is dealing with synchronizing the time of the day, the clocks among group of machines. In this case, we want to ensure that all machines can report at the same time, regardless of how imprecise their clocks may be or what the network latency are between the machines. So let's try to understand here like what is clock skew or drift here. Like that's what the clause, or that's what the thing which hinder the every computer to lag between times in second or millisecond or nanosecond. So what is clock skew and what is clock drift? So like computer clocks like any others tend not to be in perfect agreement. The instantaneous difference between the reading of any two clock is called their skew. So and in also like a crystal based clocks used in computers are like another clock subject to like clock drift, which means that they count time at different and so diverge. So underlying oscillators are subject to like physical variations, with the consequence that their frequencies of oscillations differ. Even the same clock's frequency varies with temperature. Designs exist that attempt to compensate for this variation, but they cannot eliminate it. The difference in the oscillation period between the two clocks might be extremely small, but the difference accumulated over many oscillations leads to an observation difference in the counters registered by two clocks. No matter how accurately they were initialized to the same value, a clock's drift rate is the change in the offset difference in reading between the clock and a perfect reference clock per unit of time measured by the reference clock. Now like we will try to understand like what kind of problem we can face when the time synchronization is not happen properly. So here are those some of the problems one is like real-time clock. Whenever it's synchronized in a distributed system, the process may fail because of that millisecond or nanosecond or whatever difference is. So there will be always lag, maybe because of that. Considering the case where the hardware clock are subject to drift, thus adjusted clock may drift apart as time elapses, and periodically resynchronization is necessary. Like I'll take the example, like in a Unix system, we have one command called make command, which is used to compile and modify the new code. And it may not need to recompile again because the system will check it, operating system will check it, that command clock time of that machine, and it will compile from there on to whatever files is need to be recompiled. So in this one, if the file server is at different place and your machines are at different place and your both machines are not in synchronization manner, then that command might not be produce the correct result. So it means like if both machines are different, so their timings are, if they are lagging little between, then it's like maybe it may not properly properly execute the files, and maybe you will not get that expected result. So those are some of the challenges. And also there is one more, like dividing a computational problem into multiple tasks that can be solved in parallel. That one of the reason of lacking of global time in a distributed systems are like it is impossible to guarantee that physical clock runs at the same frequency. So lack of global time can cause problem. And as I said, like in Unix example, which is the same thing example I'm showing it here. So like how can we overcome, or what is in industry standard available that is like we can use to avoid or to like overcome from this problem. So these are some of the solutions which in an industry we are using it for a distributed system. So here are those, like in a distributed system, the problem takes on more complexity because of a global time is not easily known. So the most used clock synchronization solution on the internet is network time protocol, which is called NTP, which is a layer client server architecture based on the UDP message passing. Like Lamport timestamp and vector clocks are the concept of the logical clocks in the distributed system. One other solution is like network time protocol, which is like network time protocol is like highly robust protocol and widely deployed throughout the internet. It is a well tested over the year, and it is generally regarded as the state of the art in distributed time synchronization protocol for unreliable networks. It can reduce synchronization offsets to times of the order of a few milliseconds over the public internet and to sub-millisecond levels over local area networks. A simplified version of NTP protocol is SNTP, can also be used as a pure single shot stateless master-slave synchronization protocol, but the lacks of sophisticated feature of NTP and thus has much lower performance and reliability levels. One other solution is like clock sampling mutual network synchronization. So this CSMNS is suitable for distributed as well as for mobile applications, and it has been shown to be scalable over mesh networks that include indirectly non-adjacent nodes and compatible with IEEE 802.11 and similar standards. It can be accurate to the order of few microseconds, but requires direct physical wireless connectivity with negligible link delay, less than 1 microseconds on links between adjacent nodes, limiting the distance between neighboring nodes. One other example is like global positioning system. So like in global positioning system also is used for clock synchronization, and the accuracy of GPS time signal is maybe plus or minus 10 nanosecond and is second only to the atomic clocks upon which they are based. There are also like other solutions proposed, like it's called the Einstein synchronization, where it's done by the Poincare and Einstein. So basically they invented that, and it's basically for clock synchronization at different places. They are using it, synchronizing the clock through signal exchanges. So, and this method is used like by telegraphers in the middle of 19th century, and it was popularized by Henry Poincare and Albert Einstein, who applied it to light signals and recognized its fundamental role in the relativity theory. Its principal value is for a clock within a single inter-real frame. So that is one of the solutions. Then other one is like NIDS, or we can say network identity and time zone, which is like a mechanism for provisioning like local time and date, time zone, and DST offset, as well as network provider identity information to mobile devices via a wireless network. Needs is often used to automatically update the system clock of mobile phones because the needs delivery is not usually periodic but depend on the handset crossing radio network boundaries. These handsets can be displaying incorrect time for many hours or even days before a needs update arrives and corrects them. And still there are some other solutions like this, like the Berkeley algorithm is a method of clock synchronization in the distributed computing, which assumes like no machine has an accurate time source. Internet time synchronization is like if your computer is a member of a domain and your computer clock is probably synchronized automatically by a network time server. If your computer is not a member of a domain, you can synchronize your computer clock with an internet time server. A physical clock is a physical process coupled with a method of measuring that process to record the passage of time. For instance, the rotation of Earth measured in solar days is a physical clock. Most physical clocks are based on cyclical process, such as like celestial rotations. So basically, those are the given solutions and used by the industry standard. And for using this presentation, I have used some of the references. And I think that's pretty much it from my end. Thank you so much.
Thank you. Anybody have any questions? All right. Good. Who's next?
I'll go next.
Okay, go ahead, Robert. Can you recall your presentation topic so we can?
Mine is network load balancing.
Okay.
All right, can everyone see my screen?
I can see it.
Okay. So my name is Robert Smith. My topic is network load balancing. What is network load balancing? It's a strategy for improving the scalability and availability of a distributed system. So at some point, an application will reach a point where it needs to be run on more than one server or node. So we need to distribute traffic across multiple servers in the distributed environment. A group of servers on a load balance network are referred to as a cluster, and then each server on the network is referred to as a node. It's useful for many protocols such as HTTP and FTP and others. There's a couple types of load balancers. You have hardware load balancers, which is a little bit of an older standard as we're moving towards software load balancers now. A hardware load balancer uses physical hardware to balance traffic. So on your network, there would actually be a physical machine, kind of like a switch, which would be redirecting traffic from the internet to the nodes on the cluster based on some kind of algorithm. And you got companies like Cisco and Barracuda provide these hardware load balancers. You also have software load balancers where you may have like a load balancing server or something like that on the network that would be using software to redirect traffic. This is a more modern standard because the software has reached a point where it has the same or better performance as a hardware load balancer. And then companies like IIS, well, actually in Windows Server, you have a load balancer, which we'll talk more about. And then companies like Citrix Encapsula, and there's a ton of others provide software load balancers as well. So in a distributed system, you have different types of scalability. This is vertical scalability, which is not the best. So here, your server, starting from the left, the server reaches a point where the performance is not enough to accommodate the traffic. So what you want to do is increase the performance of that server by adding more resources, more memory, another hard disk or something like that. And this is bad because you can only increase the performance of a single server up to a point. At some point, it's going to become, it's not going to be as easy to upgrade the server as it was. So this is not good because it's not infinitely scalable. It's going to, max out pretty quickly. So then we have horizontal scalability, which is much better. So it starts the same way. You have one server, and at some point, the performance can't accommodate the traffic. So what you do is you just introduce another similar server to the network. And the similar server would be running the same services, the same applications, whatever, but just in another instance. And what you do is you introduce load balancing to kind of make it appear as if there's only one instance of the application. So you have some kind of load balancing software or hardware in the middle. It receives the traffic from the internet, and then it redirects it to the multiple servers. And then once the performance of the two servers becomes not enough, you can introduce a third server, and then a fourth server, and a fifth, and so on. And you can actually reach a point where you have, dozens or hundreds, or I'm not even sure that I'm sure there is, but the limit is sky high. So you can accommodate much more traffic and increase performance much more using horizontal scalability. Balancing is what gives us that ability. So you also get increased availability with load balancing. And availability means that in the event of some kind of hardware failure, it's not a catastrophic situation, so that the application is still available in some form, and no users are denied access. There's no loss of service. So here we have a typical load balance network. You see we got 3 servers, and then there's some users connecting from across the internet, and some kind of load balancing solution is distributing that traffic. So then what happens if, say, web server 2 has some kind of hardware failure or something? Well, that server would fall off of the cluster, and the load balancing solution would account for that, and it would increase the traffic. It would redirect the traffic that would have gone to web server 2 to the first and the third web servers. So how this works is each server has what's called a heartbeat. So it's continuously sending this heartbeat signal to the load balancing software. And if the load balancing software doesn't receive the heartbeat signal, so for some reason it realizes that the server is not responding, then it accounts for that, and it stops trying to send traffic to that node. So through this, we can increase the availability of the application as a whole. So the users aren't going to notice anything here. The only thing that's going to happen is a little bit of increased traffic on server 1 and 3. So there's several load balancing algorithms. The first is round robin, which is probably the simplest. So here there's a shared IP address that is an alias for the cluster. And as traffic comes in on that connection, then it's sent sequentially to each server. So the first request goes to server 1, the second to server 2, the third one to server 3, and then the fourth one would go back to server 1. So it's just sequentially going through each node, which is the most straightforward. And then you also have a weighted round robin. So say you have one of the servers on the network has drastically higher resources or better performance than another server. You can assign it to get, say like 60% of the traffic. So then it's going to be similar to the round robin, where it's each server is kind of sequentially getting requests handling traffic. However, the server with a higher weight is going to get more requests periodically. Then you also have least connection algorithm. So the load balancing software will continuously see how many connections are being held simultaneously with each node, and it will look for the node that has the least connections at that moment, and any new connections it'll redirect to that node. Then you also have weighted least connection, and its relationship to least connection is similar as the round robin algorithms, where the traffic is redirected based on the least number of connections, but then it's also weighted so that you can take other factors into account. You also have adaptive load balancing. So each server in the pool will be constantly reporting its current load to the load balancer, and the load balancer will try to send traffic and attempt to maintain a reasonable resource usage on each node. So if one server is getting maxed out, it's doing a lot of computing, it will redirect traffic to one of the other servers to try to take the load off of that server. Then you also have chained failover. So what a failover is traffic goes to one place until that node fails. And if that node fails, then traffic starts going to the next. If that node fails, then it goes to the next, and so on. So in this method, there's going to be a predetermined order of the servers in the cluster, and traffic's going to go to the first server. And if that server should fail, then traffic will be redirected to the second. And then if that one should fail, then to the third, and so on. And then finally, you have weighted response time. So in this algorithm, the load balancer keeps track of the average response time to requests, and it'll redirect traffic based on that. So if one server is consistently given faster response time, then it may redirect traffic to it to try to get the fastest response time for the users. All right, now I have a quick demonstration here. This is actually running on my desktop computer, so I'm going to use TeamViewer here to get in. So what I have here is I have two simple web applications running in Visual Studio. These are just the default MVC applications you get when you start a new project. The only thing that I changed is the title of the web page. This one is, you can see it's server 1, and then this one is completely identical except for the title is server 2. And then I also have this load balancing software that's running. So this is it's pretty simple. It's basically another MVC application, but all it's doing is I have informed it of both nodes on the network, which is the server 1 and server 2, which are running at these 2 ports. And then also can give a percentage. So this is weighted. This is similar to a weighted round robin algorithm, and I've got them both set to receive 50% of the traffic. And then what the load balancing software here will do is just randomly redirect traffic to each server on the network based on the percentage. So one is going to get 50% and the other one's going to get 50%. And here I have it running right here. So this is actually, you can see the title up here is server 2. So you know that this content came from server 2. But you'll notice as I browse around the website, let's see, that at some point, there we go. So this page actually came from server 1. And like I said, it's random, but you'll see it's about a 50, well, it's going to be exactly 50% as I navigate See, every once in a while you get server 1 and server 2. So even though I'm sending a bunch of requests, each server is only seeing half of the activity that I'm sending. So this is just a conceptual demonstration, but you can see how the service would be split. And I can actually change. I can give one 70%, and give one 30%. So this would be how you would change the weighting of the algorithm. I start it. And you should see now server 1 should get 70% of the traffic and server 2 get 30. So you see server 1, you're going to see a lot more server 1 than server 2 now. You can see something like 7 out of 10 times it's going to be server 1. And then every once in a while you get a server 2. So that's just a pretty simple conceptual demonstration of load balancing in action. Let's see, start from all right, so because a lot of classes, especially at GSW, use Windows Azure for demonstration and IIS, and this something I think we're probably all familiar with, I decided to look at load balancing in Windows Server more in depth. This is really interesting. It's actually built into Windows Server. You can install it using the server manager, just like you would install IIS or Hyper-V or something like that. It was built into Windows Server beginning with Windows Server 2008. So if you have Server 2008 or a newer version, then it's available. Like I said, it's installed as a feature in Server Manager. And as long as you have the license for the operating system, then there's no additional charge to add the load balancing software. So you have unicast and multicast operation. That's two important choices you'll choose when you set up your load balancing cluster. Unicast is all network cards on the cluster will share the same MAC address. So this is simple. That the switch then can't locate a single node on the cluster because they all share the same MAC address. So what happens is traffic is actually broadcast to every port on the network. So then you're gonna have a lot more network activity with unicast operation. With multicast, each node is going to have two MAC addresses. So there will be the actual physical MAC address and then kind of a virtual MAC address that's provided by the load balancing software. So this way the load balancer will be able to actually communicate with each node on the cluster. So it's a little more complicated, but then you're going to have a lot less network activity. There are some disadvantages, or at least considerations. Now the advantages far outweigh the disadvantages, but there are a few disadvantages. It can be expensive. Some of the hardware and the software is not cheap. It requires a more complicated network configuration. For example, each node is going to need two network cards, one for administration. So you're going to have an IP address that you use when you remote desktop or SSH or whatever. Then you also have a network card you use because it's going to get the virtual IP address. So you need two network cards, and you have to set that up on all the servers. You're also going to have to synchronize your data. If each server has its own database, you saw in the demonstration, you're constantly being switched back and forth between different servers. So you're going to make sure that they're all sharing the same database. And then the same goes for file system. You're going to make sure, if people are uploading pictures, they upload it to one server and that's not available to the other server, then you're going to have a problem when they're redirected to that second server. And then you also have to consider that you need to create stateless applications. Now there is a thing called affinity, which if you have a stateful application, meaning that a user needs to maintain all the requests with the same server throughout the interaction, then you can set the affinity so that the load balancing software will keep sending their requests to the same server. Now, Then you also have to consider the session state. If you're holding things in the session, like with IIS, that's by default, that is stored in the actual worker process, the IIS worker process. So as the user is getting switched between different worker processes, session variables and things like that are not going to be available. And then with the IIS example, you can actually use a state server to maintain the session state. And then you're also going to have increased switch occupancy because you're going to possibly have increased traffic on the local network. So your switch is going to see more traffic. And then there's a few huge performance advantages, which, like I said, far outweigh the disadvantages. For example, you're going to see decreased CPU overhead because each node is doing much less, processing of the HTTP traffic. So you're going to see decreased CPU overhead, and then you're going to see increased throughput and response time because as requests are coming in, the server is not going to have to, you've got a queue of requests, and that queue is going to be shorter because there's less requests coming to that server. So you're going to see, faster response time and things like that. And that's my presentation. Thank you for your time.
Thank you, Robert. Did you find any good example on how databases could be synchronized?
Well, the simplest option is to just have a database server and have all of the, the servers that are providing the web application connect to that single database. You also have failover clustering for databases, which is similar to load balancing, actually, to where if all the servers on the cluster could be involved in the failover cluster. And if one server goes down, the load balancing is going to give you, availability by redirecting traffic to the other servers, but then you're also going to have availability of the database because of that failover cluster.
But if you have multiple databases in the cluster, you probably need to synchronize them to let them synchronize the data.
Right. So if you have multiple databases, then you can use something like replication.
Mm-hmm.
I think that's a little more complicated than just having the one database, though. Certainly.
All right.
Yeah, and I think with replication, I think you can only have one database that is read and write. I think the others are only read only. I'm not sure about that though.
Yeah, it makes sense.
So.
And for the session affinity, did you have a chance to discover any solutions? How it is usually implemented to synchronize, to actually make multiple requests coming to the same host, if you know that all of them are bound to the particular session?
Right. So I believe most of the hardware and the software, even with the hardware, you have some kind of console you can log into. So there is some software there as well. You can actually set the affinity on most of them. So the software will be set to redirect traffic to, to maintain the same node.
But pretty much the software has to analyze the HTTP packets to discover.
Right.
And
so in my opinion, I think the best thing would be to either have a stateless application or to have some kind of state server, like I mentioned. So that's not an issue.
Good. All right. Thank you, Robert.
Thank you.
Who will be next?
I think I'm only left. I think Colin is not presenting, so I'll go next.
Okay, go ahead. What's your title?
It's reliability of serverless distributed system.
Okay.
I'm trying to see how can I share. Where is it? Can you all see?
I can see. I'm sure
Okay,
others.
that's perfect. Good morning, all. I'm presenting today on the topic reliability of serverless distributed system. By the way, Robert, that was a very good presentation. I really liked it. So let's start. So my presentation is divided into actually 4 categories. I'll be talking about a little bit about serverless distribution first, and the advantage, disadvantage, and we'll reach to the conclusion. Okay. So the serverless distribution system, by the name itself, it is very clear that there is no any centralized server. So the server is only for the name resolution purpose. So if in serverless distribution, it is actually all the nodes and the peers, they talk directly to each other. So basically, like for example, in a team, if we have a team member, there is no any, for example, project manager. So everyone is like individually working on the project, and there is no project manager. So that kind of situation is with the serverless distribution system. Unlike in client server architecture, we have one client and one. I mean, we have a lot of clients and one server who will be handling a lot of functionality. Delegating the resources, delegating the the actions. But in serverless distribution system, we don't have any centralized server. Peers talk directly to each other, and in this server distribution system, it is owned and controlled by a single organization, and each node is owned and operated by an independent individuals who voluntarily joins the system. So that's a little bit description about what exactly is serverless distribution system. So there is a high degree of decentralization because each nodes are very powerful. Each peer are capable of doing the jobs independently. So there is a high degree of decentralization. And the peers have implement both the client and the server functionality. And so the tasks are dynamically allocated among the peers as well. So each peers has its own responsibility of providing the, of computing, bandwidth, and storage needed to operate the systems are contributed by each participating nodes. Let's talk about the advantages of this peer-to-peer system. Since each node is connected to the network, the total capacity of the system increases. For example, if we have a team and if there is a new team member that comes to our group, then the total capacity of the group will increase, the efficiency and the functionality of the group will increase. So that is the same concept. So when each node is connected to the network, the total capacity of the system increases, and there is no any single point of failure in the network, which means, like for example, if in a team one person cannot do the job, then other will take over. So because that one person is not able to do the job doesn't mean the work will not get accomplished. So there is no single point of failure in the network as well. So if one nodes fail, the rest of the nodes are able to continue the job actually. And so this type of system is actually pretty easy to install, and there is not a lot of configuration knowledge you require. It's pretty easy. For example, let's take our Skype. It's when we talk about Skype, it is one of the very good example of peer-to-peer network. It's very easy to install, right? So yeah, and there is low barrier of deployment in this P2P system. It doesn't require a lot of infrastructure. You don't need a lot of upfront investment or capital, and so that is one of the advantages of that system. That's what a lot of the companies, they also follows this kind of system because of this advantage. And you don't need full-time system administrator. Every user is the administrator of his own machines, so and user can control their shared resources. There are so the other advantage is for example, in a since each network is like very powerful on its own, so if an attacker has to attack that particular network, they must attack a very large proportion of the nodes. They cannot breach the system just by attacking one particular node. They have to come up with a very good foolproof plan. So that is one of the advantages. And so in other thing is in the P2P system, there is lots of resources that a few organizations will be able to afford individually. The resources tend to be diverse in terms of hardware, software, architecture, network attachment. And because of this diversity, it reduces the vulnerability to correlated the failure, attack, and even censorship. Now, those were some of the advantages of serverless distributed system. Now, let's talk about what are the disadvantages. When I talked about the, it's more difficult to attack the system, but there is another side of it as well. So it is more susceptible to security problems. Since every node is very independent, there is decentralization. So it is difficult to authenticate the partners and exchange the data only with the people. It's the same, like if there is a decentralization of resources, it is more difficult to figure out the problems, right? But if we have a centralized system, what happens, it is more easy to figure out the problem. So in P2P system, what happens, it's harder to authenticate the communication partner. The person at the other end is, or the other nodes, is harder to authenticate them. There is a high bandwidth usage required, which has led to internet service provider to limit peer-to-peer traffic. That is another disadvantage. Actually, one of the very good disadvantages is a high bandwidth required. In this system, the whole system is decentralized. So as I already mentioned, it's difficult to administer. More decentralization, it takes time to figure out if there is any system breach, so it's difficult to administer. So that one person cannot determine the accessibility setting of the whole network. Security in this system is very less, like viruses, spyware, trojans, etc. They can be easily transmitted over this architecture. Similarly, data recovery or backup is also very difficult. Each computer should have its own backup system. Like for example, I think everybody might have heard about torrents. P2P is the technology that is used in torrents. So a lot of movies, musics, and other that copyrighted files are transferred. It is not advisable actually to use that kind of technology to whatever is done in torrent. That is not advisable. But yeah, that kind of technology is used in torrents. Most of the P2P system or like serverless distributors they have open or loosely controlled membership. This lack of user identity allows an attacker to populate a P2P system with nodes under his control by creating many distinct identities. So because there is not much very like strict rules and regulation, members are loosely controlled. So an attacker can easily impersonate themselves and can get into the they can populate a system with a new nodes under his control and can attack the network, whole network. So that's why an attacker can defeat many kinds of defense against node failure or misbehavior. This type of system is actually good for the network which have very small number of computers. But when we talk about the big network where we have lots of devices to connect, it might not be advisable because of a lot of security reasons, and so that the sensitive data will not fall into the wrong person. So this is only good for the small number of computers or small network. Also, this kind of system also faces challenges of availability, durability, integrity, and authenticity of the data. For example, like I use Skype almost every day, and I get some random requests from random people, and sometimes the Skype doesn't work. So so those kind of things, it is little bit, those are the problems it faces. This P2P system does face those kind of issues. There is independence of dedicated infrastructures and centralized control, because of which they follow unique challenges that is not faced by other distributed systems. Even in the absence of attacks, ensuring availability can prove very difficult. For data objects to be available, at least one node stores a replica must be online at all the times. So in order to perform the whole function, at least if one node fails, there should be a replacement of that node. So a replica should be always available. So to make sure an object remains available, a system must it requires a higher network bandwidth. That's how it comes, because if one fails, the other has to come up. So it requires a lot of network bandwidth. The other thing, participants in P2P system are expected to contribute resources for the common good of all peers. However, users don't necessarily have intensive to contribute if they can access the service for free. So such users called free riders may wish to save their own disk space, bandwidth, and compute cycles, or they may prefer not to contribute any content in a file sharing system. So obviously when, if the content is free, the user will just try to save their bandwidth, their computing cycles, and they may not contribute to the whole network file system, which might not help at the end. Let's talk about some of the general application where we can use this serverless distribution system. We use it for file sharing, for streaming media, grid computing, and instant messaging. One of the popular P2P application is streaming media distribution, delivering digital television service over the internet. As in the file sharing, the idea is to leverage the bandwidth of participating clients to avoid the bandwidth cost of server-based solution. Grid computing is another peer-to-peer app that is gaining massive popularity. As I said, voice internet protocol is another peer-to-peer application. The most popular is Skype that I use almost every day. And the second one is sharing and distributing files. Presently, the most popular P2P applications are file sharing and bulk data distribution. So I'm actually at the very end of the this presentation, which is like, so how, is it really reliable or not? That is a very debatable question. Actually, it's an open question. And one hand, it adapts to a wide range of conditions with respect to workloads and resource ability. They automatically recover from the nodes of failure. There is no any single point of failure. It has a less investment. You don't have to worry a lot about the configuration. The hardware performs independently. So those are some of the benefits. And overall, it reduces the burden associated with the day-to-day operation of the systems, appear to be low as compared to a server-based solution. On the other hand, if we see at the downside, there is evidence that serverless distribution can experience wide range disruption that are difficult to manage. For example, in August 2007, the Skype overlays network collapsed and remained unavailable. So that kind of thing can happen. But fortunately, Microsoft Windows updated the patch that caused many of the peers to reboot around the same time, causing a lack of resources that combined with a software bug prevented the overlays from recovering. So this type of problem may indicate the lack of centralized control over available resources, and participating nodes make it difficult to manage the system-wide disruption when they occur. So that is all about my presentation. I hope you enjoyed it. Thank you so much for your time.
Thank you, Preeti.
Thank you.
So it seems to be we are done for today.
Okay.
There were 3 presenters, and okay. So it took us about an hour for 3 presentations. Hopefully we'll do the same on Monday because there will be 6 people presenting, if I'm not mistaken, maybe even more.
So do we need to be there as well? I think for the evaluation, right?
Yes, for evaluation, and they will be talking about interesting things. So it's not just for evaluation; it's for
okay.
the sake of you to learn something also.
Yes.
But I understand some of you have issues, personal issues, and just cannot be there at the time. So you have an excuse for that. But if you will have any chance to attend those presentations on Monday, please do it.
Sure.
Yeah.
You'll be recording the presentations Monday, won't you? So it'll be available.
There is a recording today. They will be recording on Monday,
Okay.
and today's presentation will be shared on YouTube. And I think it will take sort of an hour for the YouTube to whatever process the file, and then I will share the link.
Okay. What time is the presentation Monday?
Let me check.
I guess
It's
I can check.
1:30 to.
Okay.
Yes, it's 1:30. Yes, because
Okay.
wait, 1:30, right? 1:30 to 4:30. That'll be 4 hours.
Okay.
Thank you all. Those of you who I believe everybody except Kalyan had speak today. You can see your evaluations in FairGrader. And by the way, I would like to ask you a favor and send me any feedback if you will get anything, any bugs, issues. The system is still under development, so if you have any suggestions, maybe, or observations, send me an email with.
Simon, just one question, like, can we see our own grading also or no?
What do you mean?
Because
Your own grading?
yeah, our own presentation which we gave. So I think
That,
that we can see or no?
You mean what others? How
No, not others. Yeah, means overall, how much you got it for your topic. So
So you
something
go
that.
to the on the right corner, right top corner, you will see a menu under your name, and there are evaluations and reports.
Okay. Oh,
So
okay.
if you go to
Got it.
report, you will be able to choose
Okay.
today's presentation.
Oh, okay. Okay. Got it.
Okay.
Okay. Got it. Thank you so much, Simon.
Mm-hmm. All right. Good. So that's pretty much it for today. Thank you all again, and see you all on Monday, I hope.
Okay.
Thank you.
Thank you.